In this video, we'll be looking at writing and balancing chemical equations. The learning intention of this video is for us to learn how to balance complex chemical equations, and lastly, we're going to learn how to write as well as balance chemical equations from a worded description. Now, during remote learning, I've previously taught you how to actually balance chemical equations, okay? And we said that we needed to balance chemical equations because everything needs to follow the law of conservation of mass. But in that particular video that we've went through, we've mainly looked at examples where you really only needed to include one coefficient, meaning one number in front of a chemical or substance. So if we look at these three examples over here, we only really need to add in one coefficient to actually balance the full chemical equations. But for the purposes of today's lesson, I'm going to be showing you guys more complex chemical equations. So the first type of chemical equation that we're going to be looking at in today's lesson is where you kind of need to add in multiple coefficients to actually balance them. So in our very first example, we have to balance this chemical equation over here. If you guys can recall, I previously showed you this particular table over here as a way for you guys to actually show full working out to balance your chemical equations. But obviously, if you guys are confident, you don't have to do this at all. But for the purposes of this video, I'll show you the full working out. So in order to do this particular method, you just list down all the elements that's present in the chemical equation. And once you've done that, you'll just count the number of atoms for each element in your reactants as well as your products. So on the reactant side, so the left-hand side, we can clearly see there's only one aluminium, there's 3 bromine atoms, there's 2 potassiums, 1 sulfur, and there are 4 oxygen atoms. On my product side, we can see that there are 2 aluminiums, there's 1 bromine, there's 1 potassium, and in this case over here, this is where people often get confused, but because this is a sulfate ion, and there are 3 of them, that indicates that there are in total 3 sulfur atoms, and there is a total of 12 oxygen atoms, because one sulfate ion has already 4, but because you've got 3 groups of them, therefore you will have 12 oxygens in total. Once we've done that, then we just need to see which ones are balanced, and we can clearly see that none of these are balanced over here. So let's firstly balance aluminium. To balance aluminium, what we need to do is we need to add in an extra aluminium on my reactant side to balance it so that there's 2 in total. So what I'll do is I'm going to add a 2 coefficient in front of aluminium bromide. So by adding a 2 over here, this now adjusts the number of aluminiums to 2, but this will also change the number of bromine atoms as well on my reactant side. So therefore, there's now a total of 6 bromine atoms. Once I've done that, what I'll do next is I'm now going to balance the number of bromines, okay? Now, what I will do in order to balance the number of bromines is I'm going to add in more bromines to my product side. So therefore, I'm going to be adding more potassium bromide. So what I'll do is I'll add a 6 coefficient in front, and by adding a 6 in front over there, I'm now going to have 6 bromine atoms, but I'm also going to be changing the number of potassium ions as well. So therefore, the number of potassium atoms in this case is also going to be 6. So now what I'll do is I'll balance the number of bromines on my left-hand side, on my reactant. So therefore, I'm going to add a 3 in front of this particular compound over here, which is potassium sulfate. And by adding a 3 in front of here, this will therefore balance the number of potassiums, but it'll also change the number of sulfur atoms as well as oxygen atoms. So now there is 3 sulfur atoms, and there's also now 12 oxygen atoms. And as you can see over here, by adding a 3, this actually balances everything else. And now our chemical equation is now balanced. So if I was to rewrite the whole thing, this is, remember, a default 1. So in this case, this would be our final answer over here. So just to get more practice, I advise you guys to actually answer all of these questions, but leave this to the end of the video because I'm now going to be moving on to the next part. So I'm now going to be showing you how you can actually balance chemical equations by using fractions, okay? Now, this particular chemical equation is a bit different from other chemical equations, so I want you guys to actually pay attention as to what I'm actually doing. So we're still going to be doing the exact same process again, where you would generate this table and list down all the elements that's present. And then again, similarly, you will therefore count the number of atoms present in your reactants and products. Okay, so this is pretty straightforward over here. Now, for this particular example, we can clearly see that the number of potassiums as well as the number of chlorine atoms are already balanced. So all we really need to do is balance the number of oxygen atoms. However, if you guys actually try to balance the number of oxygen, you can't really add a coefficient in front of this oxygen molecule at all, because by adding any whole number, it's not going to give you an answer that gives you 3, okay? So any whole number integer won't multiplied by 2 already won't give you 3 at all. So that's what I mean by adding a coefficient in front of O2 won't give 3 oxygens, since any number multiplied by 2 will give you an even number. So what you actually need to do instead is that we're therefore going to think of a decimal or fraction that when multiplied by this 2 over here, okay, or this 2 over here, gives you an answer of 3. Now, if you guys are pretty solid with maths, you guys would recognize that if you multiplied 2 with 1.5, therefore that would give you 3. So therefore, if I add a 1.5 here, that would therefore balance this chemical equation, okay? So therefore, this would be pretty happy over here. However, you guys probably already recall that chemical equations must only contain whole numbers. You cannot possibly have a fraction or a decimal at all, as you can't really have half of a molecule. It just doesn't make any sense at all. So in order to kind of avoid that, what we need to do is therefore multiply our entire equation by 2. And if you multiply the entire equation by 2, you won't actually have these decimals or fractions at all. So I'll show you what I mean. So if we multiply everything by 2, because that's a 1 already in front of these two substances over here, 2 times 1 becomes a 2, so therefore 2 comes over here, and 2 also comes over here, and 1.5 times 2 gives you 3. And now if we do this, the entire equation is not only balanced, but it only now contains whole numbers. And you could also count the number of atoms as well to double check this. I'm now going to be showing you guys another method of how you can actually balance this particular chemical equation, and that's by using a visual approach, okay? Now, using this visual approach is not really recommended if you're doing this for your test at all, because it would be a bit time consuming. So to do this visual method, what you need to do is you just need to draw each of the individual substances that's listed in the chemical equation. So I've done that as you can see over here. Once we do that, then we need to balance this chemical equation. We can see that potassium and chlorine are already balanced, so we don't have to worry about that, but we just need to balance the number of oxygens. So because there's more oxygens on the reactant side, I'll have to add in more oxygens to my product, so I'll add in an extra molecule of oxygen over here. But if you guys actually do that, we can see that the number of oxygen is still not balanced. There's more oxygens now on my product side than the left-hand side. So in order to do that, we'll have to add in more of these guys over here to balance the number of oxygens. So by adding an extra compound of this particular potassium chlorate, we can clearly see that the number of potassium as well as chlorine and oxygen is now unbalanced. So in order to combat that, okay, because we now have more atoms on the left-hand side, we'll have to therefore balance the number of potassium and chlorine again. So what I'll do is I'm going to add in an extra compound of potassium chloride, and by doing so, this would now balance potassium and chloride. But again, the number of oxygen is still unbalanced. So what I'll do is I'm going to add in an extra molecule of oxygen gas. And by adding an extra molecule of oxygen gas, therefore this will balance the entire chemical equation. So this particular visual method over here, as you can see, didn't involve using fractions at all. But if you were to actually use this method, it would just be a bit more time consuming. So I want you to now have a go at answering this particular chemical equation over here. Give yourself 3 minutes and then we'll compare our answers together. So my first step is to count the number of atoms for my iron atoms and oxygen atoms for both the reactants as well as the products. So I've done that, as you can see over here. So what I'm going to do is I'm going to balance the number of Fe ions, okay? So by balancing the number of Fe ions, I'll just add in an extra Fe over here, and therefore this will become balanced, okay? So that's pretty good. And all I need to do now is balance the number of oxygens. We know that 2 multiplied by any number won't give you 3 at all, so therefore we will have to use the fractions. So in this case, 2 times 1.5 is going to give you 3, so I'm going to add a 1.5 in front of here, and now the number of oxygen atoms is balanced. Remember, we can't actually use fractions at all, so I'll have to multiply everything by 2, okay? And by multiplying everything by 2, therefore this will balance the entire chemical equation. So therefore, instead of having a 2 in front of Fe, that will now become a 4. This would now become a 3 in front of oxygen, and therefore there'll be a 2 over here, and therefore that would be your final answer. What I'd like you to do now is I'd like you to please answer these questions over here to get extra practice where you have to actually use fractions in order to balance this chemical equation. We're now moving to the last part of today's lesson, where you're going to be learning how to write chemical equations from worded description. So in order to do so successfully, you need to be familiar of the four physical states of matter. It could either exist in the solid state, the liquid state, the gaseous state, or the aqueous state, okay? And in order for you guys to recognize what state each chemical substance is in, you're going to need to use a bit of your prior knowledge and a bit of your common sense. So for instance, what I mean by that is if you see the chemicals oxygen, carbon dioxide, carbon monoxide, those kind of substances, that should already tell you that that's already in the gaseous state, because you should already know that most of these molecules or non-metals generally exist in the gaseous state, and things such as water, we should know that's going to be in the liquid state, okay? You could also need to actually look and recognize some key words. So what I've done is actually I've generated a table over here to show you some of the associated words with each of these four states of matter. So for instance, if you see the word precipitate, pure metal, solid, ribbon, then that should automatically tell you that that substance is in the solid state. If something's in the liquid state, it will either be the word melted, concentrated for gas, you would see the word steam, bubbles, and for aqueous, which means dissolved in water, it will mean soluble, diluted, or solution, okay? Generally, you will see the word solution, so just be familiar with these words and what state it's actually associated with. Another way to tell what is the physical state is by looking at what type of compound is it. Is it an ionic compound or is it molecular? We know that ionic compounds have strong electrostatic forces of attraction, so generally speaking, that could either be in the solid state or it could either be in the aqueous state because it can be dissolved in water, okay? But for a molecular compound, okay, so a compound that's just composed of non-metals, then generally speaking, they will generally be in the gaseous state or in the solid state. So you kind of have to predict what is its melting point going to be. And lastly, for ionic compounds, you need to refer to the solubility table to see whether it exists in the solid state or in the aqueous state. But that's more for VC knowledge, so you don't really have to worry about this. For now, we're just going to be looking at the keywords to actually write and balance chemical equations. So I'm going to go through two examples over here. So for the first example, it reads, aluminium metal reacts with aqueous copper 2 chloride to produce aqueous aluminium chloride and copper metal. Now, in this particular example over here, this is a metal, so that's Al in the solid state, and it's reacting with aqueous copper 2 chloride, okay? So you have to know how to write the chemical formula of this substance over here. So copper 2 is this, chloride is this. So remember, do the crisscross method. So therefore, it's going to be CuCl2. And because in the aqueous, you have to write AQ here. Aluminium chloride is going to be AlCl3, if you guys remember. And that's going to be AQ. And copper metal is just going to be Cu solid, okay? So therefore, this is pretty much what your unbalanced chemical equation is going to be. So you now need to actually balance the chemical equation. So we can clearly see that aluminium is very balanced, copper is balanced, but the number of chlorine atoms is not balanced, okay? So therefore, in order to balance this, what I'll do is I want to add in a 1.5 in front because we know that 1.5 times 2 is going to give you 3, okay? But remember, you can't have fractions at all or a decimal, so I'll multiply the whole thing by 2, and by doing so, this is going to be the balanced chemical equation for this word description. For my second example, it reads solid lead 4 sulfide, okay, so that's in the solid state, reacts with oxygen gas, so gaseous state, to produce solid lead 4 oxide, so that's going to be solid state, and in this case over here, sulfur dioxide, that's a molecule, okay, only containing nonmetals, so that's going to be in the gaseous state. So therefore, if you're going to write it, this is what your unbalanced chemical equation should look like, and therefore we just need to start balancing it. So in this particular example over here, the number of sulfur atoms as well as the number of oxygen atoms is unbalanced. So what I'll do first is I'll balance the number of sulfur atoms by adding a 2 in front of the sulfur dioxide. By doing that, this will also change the number of oxygen atoms. So at the moment on my product side, there's 2 and there's 4 oxygens in total. So therefore there is going to be 6 in total on the right hand side. And over here there's only 2. So therefore I'll add in a 3. So that's going to be my final answer. Now that I've gone through these two examples over here, I'd like you to please answer these following questions. As you can see, there are a number of questions that I'd like you to answer, but in order for you guys to have complete mastery of this, you actually need to do a lot of practice. So please do these questions over here. Thank you guys for watching. This is the end of today's video. I'll see you guys again in the next video. Bye.